Okay, let's get started. Any questions so far? Any questions? By the way, just based on your friends' questions, these honest and dishonest, well, the honest part doesn't have any problem, but the dishonest. So when we say dishonest, we don't mean that the expert always tells the opposite. The expert behaves, given the situation, in a way to, improve his welfare. So, if the problem is a major problem, okay, then it is in the interest of the expert to report it as a major problem. Okay? But if it's a minor problem, okay, an honest expert would say the problem is minor. A dishonest expert would say the problem is major. So the honesty part matters when the problem is a minor problem. Behaving honestly when the problem is minor, behaving dishonestly when the problem is minor. Okay? So we've simplified notation with simplified wording. So when I say honest, dishonest, okay, honest when the problem is minor, honest, dishonest when the problem is minor. The same is true for the consumer, accept, reject. Okay? So if the expert said, the problem is a minor problem and I'll charge you a minor problem fee, would the consumer ever reject this offer? If he accepts, he's going to pay I. If he rejects, he's going to look for an outside option, which would cost him I prime, which we assumed is bigger than I. Okay? So, okay, a consumer will never reject a minor repair fee. Okay? Okay? But if the expert said you have to pay a major repair fee, well, as a consumer, the first thing that would come to my mind is, well, it might be really a major problem. What did I say in a few minutes? If the expert said it's a major problem, so you have to pay the major problem fee, the immediate thing that I would think is, he's honest, and if I go out for an outside option, I'll have to pay E prime, but he might be dishonest. So even though he says it's a major problem, it might be a minor problem. And if I look for an outside option, it will cost me less in that case. Okay? So the accept, reject only makes difference when the expert says you have to pay the major problem fee. Okay? So the consumer will always accept the minor problem fee because that's the best he can get. Okay? So based on this, let's fill in this box. So the expert is honest, and the consumer rejects. But what does he reject? He rejects a major problem fee. He accepts a minor problem fee. So A here again says, accept a major problem fee, accept a minor problem fee. Reject here means accept a minor problem fee, reject a major problem fee. Because in both cases there is accept minor problem fee, accept minor problem fee, we don't write that. If something is common, okay, then you don't have to write it. Just keep it in mind. Okay? So, based on that, what is the expected payoff? Which one do you want to start with? Expert or expert? What is the expected payoff of the expert? 1 minus. Okay, well, let's go step by step. So with probability R, the problem is going to be a major problem. And he's honest, so we would say it's a major problem. In that case, The consumer which uses this strategy will do what? Will reject offer and look for an outside option. In that case, the expert's profit is going to be 0. Okay? But with probability 1 minus R, the problem would be a minor problem. And hence, an honest expert would say it's a minor problem. In that case, a consumer which uses this strategy will do what? Accept offer. If he accepts the offer, what is going to be the profit of the firm? Of the expert? It's going to be pi. Okay? So it's R times 0 plus 1 minus R times pi. Or just simply, as your friend said, 1 minus R pi. Yes, question? The consumer's expected payoff? That's what you were, no, you had a question, or I'm sorry. So with probability R, problem is major. An honest expert will charge E for it. Okay. We'll say you have to pay a major repair fee. Okay. But we said our consumer is using this strategy. And what did this strategy say? Reject any major repair fee. So consumer rejects, in this case, when the expert charges E, the consumer rejects the offer. In that case, how much money would you win as an expert? 0 in, 0 out. Your profit is 0. So with probability R, you'll earn a profit of 0. With probability 1 minus R, the problem is going to be a minor problem. And as an honest expert, I'll say the problem is a minor problem and I'm charging you E. What does that consumer do? Accept. He accepts, right? Because that's the lowest that he can get. He accepts. So if he accepts, what is my profit? Okay, so fixing a minor problem and charging a minor problem fee gives us a profit of pi. Okay, that's the expected payoff. So it's not actually this, it's plus 0 times R. Okay? Okay, so far so good? Actually, let's write it properly. So sometimes putting these things are important because it tells you what's happening. So actually, let me use it symmetric. R times 0 plus 1 minus R times pi. Okay, even though R times 0 is 0, putting it there tells you on how you came up with that number. So people might be confused with this, but this is clear, and it's more symmetric. So actually, I should have said here, R pi plus 1 minus R pi. So what is the expected payoff of the consumer? So we'll put the minus because everything will be negative. So with probability R, the problem is going to be major. The expert will tell me that it's a major problem. And then I reject major problems. So what happens? I take the outside option, but the problem is a major problem. So the outside option cost me E prime. So that's R times E prime, right? But with probability 1 minus R, it's going to be a minor problem. And the honest expert will charge me the minor problem fee, right? And I will accept. I always, the consumer always accepts a minor problem fee. So he will accept it. So the cost to him would be I. So that's the expected payoff. When the expert is honest and when the consumer always rejects the offer. Okay? So far, so good? Yes, sir.
But why do we accept when the outside option is more costly when we have a major problem?
In which, yeah.
Right? Yes, we have E prime. Why don't we reject paying E prime and pay E?
Well, the thing is, you see, we're taking the average, the expected value of it. So I'm not sure, you see, with some probability it's going to be a major problem, and it's going to be E prime, but with some probability it's going to be a minor problem. And if I accept it, that's what I'm going to pay. Okay? So E could be less than their average, you know, their weighted average, or bigger than the weighted average. Okay? Yes, sir.
We are writing this box under reject, yes. So how we...
Again, reject means rejecting a major repair fee. The consumer never rejects a minor repair fee. Okay?
Then R means...
R is the probability that you're... Oh, that's, again, reject. So again, so if I wanted to write it the long way, accept all fees except minor repair fee, reject major repair fee. What a handwriting. Okay. So since except, you know, well, let me write this also. Except minor repair fee, except major repair fee. Okay? So except minor repair fee is here and also here. So if something keeps appearing always, you really don't have to write it. You just keep in mind. Okay? So we're lazy. I say I'm not going to write this because it's always there. No matter which column I'm looking at, it's always there. So don't write it, but keep it in your mind. What is different is accepting a major repair fee, rejecting a major repair fee. That's what's different. That's why I just write these. Okay? So far, so good? Again, accept means accept whether the fee is a major repair fee or a minor repair fee. Reject means accept a minor repair fee. He can't pay less than that. Okay? Accept a minor repair fee, but reject a major repair fee. Okay? That's what reject means. Okay? So far, so good? The same thing here. Honest says, tell that it's a major problem when the problem is major, and tell the consumer that it's a minor problem when the problem is minor. Dishonest means tell the consumer that the problem is a major problem when the problem is major. Tell the consumer that the problem is a major problem when the problem is minor. So again, we erase what is common and just write what is different, but keep in mind what is common. We're being lazy, saving ink. Okay? So far, so good? So, 3 down, 1 to go. What is the payoff? So a dishonest expert says, always charges a major repair fee, and a consumer which uses this strategy always rejects a major repair fee. So his expected payoff is 0. The expected payoff of the consumer with probability R, it's going to be so because the expert said it's charged a major repair fee, irrespective of the condition of the computer, okay? So he always takes the consumer always takes the outside option. With R probability, it's going to be a major problem. which when he takes the outside option will cost him E prime. R times E prime. Of course, that's a cost, so we put the minus. And with 1 minus R probability, it's going to be a minor problem, and the outside option will cost him I prime. So that finishes modeling the game. Now, we're done with modeling. We can solve for the Nash solutions. So what do you do? So give it a try. That's a 2 by 2. It's a simple case. No matter which method you use, you should be able to find. So you can use the two graphical methods that we had, or you can use the theorem that we had. Let me try to write this a bit cleaner. So let me write, so R was a number between 0 and 1. Pi prime is bigger than pi. And then E prime is bigger than E, which is bigger than I prime, which is bigger than I. That's what we have. So the game accept any fee, reject any major repair fee, but accept minor repair fees. Be honest. Tell when the computer has a major problem, report it as a major problem. And when it's a minor problem, report it as a minor problem. So the payoffs, the expected payoffs are pi minus R E minus 1 minus R I R pi plus one minus R pi prime, and then minus E. One minus R pi minus R E minus minus R E prime so a bit, did I make a mistake somewhere?
In top right.
Oh, yes, yes. He rejects. Thank you. Okay. Well, a bit better handwriting, but still way much worse than what Semih Hoca has. By the way, my master's supervisor was Semih Hoca, who was also instructor here. I learned a lot from him. His handwriting is perfect. It's he didn't use computers for quite a while because his handwriting was so good that, we would just write them and we'd just photocopy them. And my PhD supervisor was William Thompson. He draws perfect pictures, but his handwriting is impossible to read. So mine is almost infinitely better than William's handwriting. So and almost infinitely worse than Semih Hoca's. Yeah, so I'm kind of a complex combination of at least in this sense, of my two supervisors. Okay, so did anybody find the Nash solutions? No? So, you want more time? No, yes, maybe? Or you have an answer?
Honesty and reject major. I think that's the Nash.
So, come again?
H and
H R. That is, so we're looking at the, so again, so if we're not looking at the mixed extension game, we have to compare this number with this number. Okay. By the way, what is the comparison? So what is the comparison between these two numbers?
Since we're taking a linear combination of pi and pi prime, and since pi prime is greater than pi, the one below is greater than
Exactly, right? So this is a convex combination of pi and pi prime. And we know that convex combination is always greater than or equal to the smaller. Okay, well, since the weights are positive weights, the convex combination is always greater than the smaller weight, smaller number, and less than the greater number. So the smaller number here is pi. So we know that this number is greater than, so r pi plus 1 minus r pi prime is greater than pi. So in the pure strategy game, D is a best response to A. What about these two? Well, pi is a positive number. We assume that r is less than 1, so that's a positive number. So H is a best response to R in the pure strategy game. So that was easy. What about player 2? A is a best response to H, right? So here, this and this are the same, so essentially cancel them out. So what you're comparing is RE minus RE and minus R E prime. We said E prime is bigger than E, so minus RE is bigger than minus RE prime. So A is the best response to H. Okay. So here it's more problematic. You see, we're taking a convex combination of E prime and I prime, and we're comparing that convex combination with E, well, with the negatives. Well, if the weight on E prime is higher, okay, in absolute value, this number would be bigger. So it means that this would, A would be a best response. But if there's a lot of weight on I prime, so if R is close to 0, okay, then this number, did I say it correctly? Yeah, okay. So depending on what E prime, E, I prime, and R is, in the pure strategy game, A could be a best response to D, or R could be a best response to D. So we don't know. Depends on E, R, E prime, I prime. Okay. But let's look at this case if, so by the way, HR is not. But you see, you give it a try. Okay, making mistakes is okay. Not trying is the worst thing that you can do to yourself. So, if the pure strategy game, if there is any hope for the pure strategy game to have a Nash equilibrium, it's the only thing could be D, A. Okay, so for that to happen, A should be a best response to D. So for that to happen, minus E should be greater or equal to minus R E prime plus minus 1 minus R I prime. So if we arrange the terms, how do I want to? Oh, let me just write E is less than or equal to R E prime 1 minus R I prime. So if this is the case, then the Nash equilibria of the game, of the pure strategy game, is D A. So essentially, you should always use your intuition too, okay? So if the outside option is always too costly, on average, okay? If the expected value of the outside option is too costly, or the cost for a major fix is not too costly, what would you do? As a consumer, you would always accept, right? And if you're always accepting, what is the best thing for the expert to do? Be dishonest, okay? So this essentially says the cost of the outside option is when it's high, the consumer always accepts the offer. Pretty intuitive. So let's look at the case when E is greater than R E prime 1 minus R I prime. In that case, R is a best response to D. Hence, the pure strategy game, the original game, does not have a Nash equilibria. So we look at the mixed extension game. So what do you do there? Well, you can use the graphs or you can use the theorem that we had. So maybe let's make use of the theorem. So far we've been always using pictures. Let's do a difference. Let's give names to these things. So rather than writing mu1h, mu1d, mu2a, mu2r, let's simplify notation. Let's call this P, this 1 minus P, this Q. So what I mean is by saying this Q, the mixed strategy at which A is played, the probability at which player 2 plays A will denote with Q, and hence R will be played with probability 1 minus R. Okay. So yep.
Each of the strategies of each player is the best response to S minus I. Then we say that both strategies of each player are in the support of mu.
Are in the support of? Well, but.
So P should be greater than 0.
So wait a minute. What was the explanation again? Come again?
With the theorem we had,
Mm-hmm.
we said that if a strategy is dominating, I mean, it's not the best response.
Is never a best response, or is not a, which one are you talking about?
It's never a best response.
Mm-hmm.
Then its probability is 0. If
Okay.
it's the best response, then it should be
Okay.
played with
So in this game, is there a strategy of player 1 which is never a best response? Okay. So no. Well, obviously, H is a best response to at least one strategy of player 2, and D is a best response to at least one strategy of player 2. So player 1 does not have a strategy which is never a best response. So what is the conclusion that you get from there?
P is greater than 0, but less than
P is greater than 0, but less than 1. Does everybody agree with that conclusion? So what did we have in the first lecture? We said if a strategy is never a best response, then that pure strategy will be played with probability 0 at any Nash equilibria, right? So using this fact, your friend concludes that H and D should be played with probability greater than 0. Everybody agree? Vice versa might not be, right? The statement that we had is an if-then statement. If it's never a best response, then it's played with probability 0. It doesn't say that if it is sometimes a best response, it's played with probability bigger than 0. Okay? So if never a best response, then at any Nash equilibria, that strategy is played with probability 0. Okay? But it's an if-then statement. So if the hypothesis part is true, the conclusion part has to be true. If the hypothesis part is false, that is, if a strategy is not a never best response strategy, then the conclusion could be true or false. That is, that strategy at some Nash equilibria could be played with probability 0 or could be played with a positive probability. So just based on that, we cannot say that H is played with positive probability and D is played with positive probability. But let's use that theorem, we're going to use the support thing. So let's consider the case where, so let mu1, well, let PQ, rather than writing P1 minus P, Q1 minus Q, I'm just going to write the first elements of the mixed strategies. Bn, B. Let me just write this mixed strategy profile such that support of P is equal to HD. Yes, sure.
If a pure strategy is a best response, it means that it is played with probability 1.
If a pure strategy is a
Best response.
it's played with?
Probability 1. We say that it's played with probability 1.
No, it doesn't have to be. You see, in the examples that we had, for example, the Battle of Sexes game. It had 3 Nash equilibria. Okay? 2 of them were pure strategy Nash equilibria, and 1 of them was a completely mixed strategy Nash equilibria. So even though going to, what did we use, ballet or opera? I forgot. Opera, okay? So even though going to opera is a best response to some strategy of the opponents, it's not played with probability 1 at some Nash equilibria. Okay? So far, so good? So if the supporters P is equal to H and D, that is if H and D are played with positive probability under the mixed strategy P, then this will be a Nash equilibrium if and only if the expected payoff of player 1 from playing P should be equal to, from playing H should be equal to the expected payoff he gets by playing D, right? So let's write that. Expert E, well, let's call it 1. So player 1 is expert in accord with the convention that we have for tabular representations. H, when the second player is playing Q. Again, we're abusing language, right? So when I'm using H here, this is not like a mixed strategy. So when I say H, what I mean is H is played with probability 1, D is played with probability 0. That should be equal to U1 of DQ. But U1 of H is equal to q times pi plus 1 minus q times this animal. So q pi plus 1 minus q times 1 minus r pi. So here it's q r pi plus 1 minus r let me put the q here, pi prime. Right? I hope I did not make any mistakes. Yeah, so q times pi plus 1 minus q times 1 minus r pi. Q times r pi times, where is that? Oh, yeah, q times, yeah, well, plus 1 minus q times 0. So, what does that imply? What does that give us? So let's simplify things. I'll expand this. That's some part that, well, let's put all the pi factors on one side, put q here. So there we have q plus 1 minus r minus q plus rq. And then we took this to this side. So that becomes minus rq is equal to q1 minus r pi prime. This and this cancels. This and this cancels. So we have 1 minus r pi equal to q1 minus r pi prime. So 1 minus r cancels. Q is equal to pi prime. Okay? Both pi and pi prime we assumed are positive. I forgot to write that here, but they're positive. And pi is less than pi prime. So actually this is a number between 0 and 1. Okay? So if PQ is a Nash equilibrium under which both H and D are in the support of P, then Q has to be equal to pi over pi prime. That is, the consumer should accept any offer with probability pi over pi prime. Okay? So far, so good? Well, because Q is greater than 0 but less than 1, what does that imply? A and R in the support, exactly. So let me use this part. Well, if both A and R are in the support, then the expected payoff that player A will get by player 2, the consumer will get by playing A, should be equal to the expected payoff that the consumer would get by playing R. So that would be the case. That would imply, well, U2 of PA equal to U2 of PR. So what is U2 of PA? So P times this animal plus 1 minus P times this. So let me put the minus sign here. P times RE plus P times 1 minus RI plus 1 minus P times this animal, E. That's the left-hand side. The right-hand side, take these. So P times, again, put the minus P times R E prime plus P times 1 minus R I plus 1 minus P times E prime plus 1 minus P times 1 minus R times I prime. So the negatives cancel each other. Okay, so what do we have? First, PRE, no, that's PRE prime. They don't cancel. So is there anything that cancels? So, so that's with that. Anything else? That's not. Okay. So let's see. Let me try to put all the p's on one side. You see I'm trying to solve for p. Yep. Did I make a mistake somewhere?
The right part it is 1 minus p times r.
You forgot the R.
Oh, forgot the R there. Yeah, thank you. Thank you. Yeah, there was the R there. Okay, so RE minus E. So there's the E, which goes to this side as minus. Okay, so we took care of this. We took care of this. So let's move that over here. Minus R E prime. Took care of this. So plus E took care of this part. Take that to the other side. P R E prime. That's E prime, by the way. So took care of this. Sorry? P R E prime.
You already factored out P, so you don't have to.
Oh, yes, yes, thank you. Okay, yeah, the P was factored out here. And then from here, we have, so minus becomes plus 1 minus R E prime. That's equal to plus 1 minus R E prime. Right? I hope I did not make any mistakes.
Jump to the right side. Should it be R E prime?
Which one?
Second one to the right. Should it be R?
No, that's, so we had 1 minus P, R, yes, yes. E prime, yes, there should be an R. Thank you. Okay? Any questions? I was thinking that it should look, oh, so RE prime minus RE prime, so those two cancel. Anything else canceling? Can anybody see anything? No, I guess that's it. So P is equal to E prime minus E plus 1 minus R I prime divided by, I keep forgetting the R, yeah. E prime, yeah, yep, yep. Okay, divided by, so 1 minus I prime, so minus, oh, let me write it as R minus 1 E. Okay? Any questions? Yep.
Since E prime is greater than B,
Yes, we took E prime greater than E.
greater than B,
Sorry?
is greater than B.
This number is greater than 1. Yeah, this thing is. Boom. So maybe doing somewhere in the arithmetic, I made the mistake in some of the cancellations. So actually, let me write down what? Where did I make the mistake? Yep. Mm-hmm. No, with this is definitely bigger than 1. So it could imply two things. One, there's no such P. Okay, there is no Nash equilibria where. So how do we arrive to this conclusion? We arrive to it by assuming that both H and D was in the support. So there's no mixed Nash equilibria where both H and D are in the support, or the other conclusion is I made a mistake, which is the most likely case. So actually, let me write down, luckily, so this is one instance. It's not high math, but when you write these things, you have to write them carefully and go step by step. In canceling, I probably, in the rush, canceled out something fast. So let me write down what actually Osborne finds, which is very similar, but except with a problem. So this side is the same. This side actually is the negative. So I maybe messed up the signs somewhere, but I can't see where. Anyhow, check the signs. So maybe I did mess up with the signs somewhere.
It's the same thing. You multiply by -1. Both of them. Denominator, we have the same result as before.
Oh, yes, it's the same. So what do we have here? Well, that's less than. So if I put an E prime here, that's less than 1 minus R E prime minus I prime divided by 1 minus R E over I. That doesn't say much. But this is, oh, yes, I'm sorry. Yeah, I made a mistake here. It's less than 1, definitely. So replace this with a smaller number. You get something bigger because of the negative sign. So it's 1 minus R E minus I prime divided by 1 minus R E minus I prime, which is equal to 1. So this number is definitely less than 1. Okay. Is it greater than 0? Well, if you remember, the way to eliminate this Nash equilibrium was this number was less than this number. So if we assume that, this animal becomes positive. So that's a number bigger than 0. Okay? So sorry about the mistakes there. So we'll pick up from here next lecture. The important thing is, finding Nash equilibrium, mixed range Nash equilibrium is just in a 2-by-2 case. It's just simple algebra. All you have to do is be careful about the algebra, okay? But once we have this, the nice thing about this is we solved it parametrically. And once you solve a problem parametrically, like the question in the homework, you can ask interesting questions. You can ask, what would happen if R increases? That is, the number of computers with defective major problems increases. What happens if the cost of outside option increases? So you can ask questions like this. And that's what we'll do. And then we'll start talking about correlated equilibrium next lecture. That's it.